Hey guys, and welcome to the third video in our EKG lecture series. This one's a quick talk about electricity, and my name is Shelton Coco, and welcome. Thank you for joining me today. In this video, we're going to talk a little bit about electricity. We're going to talk about it, where it comes from, where it goes, and how we can read that on the 12 lead. And then we're going to make some generalizations that are going to help us later on in pattern recognition. That's especially going to help us when in our next video we look at specific patterns that are characteristic for specific diseases. So let's get started. Well, we know that the heart uses ions like sodium and potassium to produce electricity. And it does that by allowing those ions to flow in and out of the cell, and that flow produces the electricity needed to start the process of contraction. And so the more muscle that's used, the more ions are flown or that move through the cell, the cardiac muscle. And if the more ions that are moved, the more electricity that's produced. And we're going to see this little tidbit of knowledge comes in handy when we start looking at 12 leads and we're starting to characterize where the electricity is flowing, and that starts to equal which part of the heart is working harder. So let's begin that journey, man. Alright, we know that the electrical source of the heart is typically in that right atrium, in that SA node. And we know that the electrical activity typically moves in an inferior manner towards the ventricles. And since the left ventricle has more muscle than the right ventricle, and if it has more muscle, it moves more ions, which means it has more electrical activity, it has a more dominant electrical presence, then we know that the electricity also moves a little bit towards the left. And if we were to draw the average movement of electricity, it would look something like this. A little down and a little to the left, originating in that right atria. And in fact, we're going to see that that's exactly what we see on the 12 lead. And so if things start to change, so for instance, if the electrical activity of the heart maybe is moving this way, not towards the left ventricle, we're going to start to be able to say things about the right ventricle based off the activity of the electricity that we see on the 12 lead. Now, the one hurdle that we have to overcome, though, is how do we as clinicians describe this change in the average electrical movement to other providers? What basis or what standard of measurement do we have that we can use? And so if we think about this, we'd probably come up with a system similar to the idea of drawing an axis, like in a graph, that separates the right and left side and the top and the bottom, the atria from the ventricles. And we would see that the average flow of electricity falls somewhere between this 0-degree mark and this 90-degree mark. In fact, the average is about 60 degrees. And so we have 0 degrees over here towards the left, 90 degrees inferior. And we have about 180 degrees over here, and negative 90 degrees up here. Well, now we have a very convenient way to be able to describe the average flow of electricity in the heart. So for instance, if we said the average QRS vector is, let's say, negative 45 degrees, well then we know that we're looking at electrical vector that's in this movement. And that tells us both the start or the originality of the electrical source and the destination. So if we have a QRS complex that is negative 45 degrees, that is highly suggestive of a ventricular rhythm. That's pretty cool. And we're going to see how we can start to quantify these angles and how they can fit into certain disease patterns. So let's look a little deeper. Since we now are familiar with the average electrical movement of the heart, and the idea that this average electrical movement can be described in terms of angles. Let's see what else we can build from that. One of the things that we have to become familiar with is this idea that there's 3 reference points for the electrical view of the heart. Right? So let's look at lead 2, for example. Lead 2 looks at this part of the heart, right underneath, a little towards the left. And we know that the typical lead 2 is a positive P wave, a positive dominant R complex, and a positive T wave. And we see that the average electrical movement, this green arrow, is towards lead 2. And we know that AVR, this typical complex on the 12 lead, is a negative P wave, a negative QRS complex, and a negative T wave. And we notice that the average movement is away from AVR. So we can start to characterize things based off of where the electrical activity is flowing and which lead is looking at that electrical activity. And we see that when electricity is moving towards the electrode, we get a positive complex. Just like how in lead 2, under normal circumstances, is predominantly positive. And when the electricity is moving away from the electrode, we get a negative QRS complex. And we know that to be true because in our previous video, we talked about how AVR is a predominantly negative everything. The P wave, starting up here, moves away from AVR. And the ventricular activity, starting in the AV node, moves away from AVR. So negative P wave, negative QRS complex. Now the thing that is slightly less obvious, however, is when something moves past the electrode. So let's take a look over here at AVL. We see under normal conditions, the P wave begins, and if we draw like a perpendicular line, we see that the P wave, the atrial activity approaches it and then passes it as it moves through the ventricle. Excuse me. And so we can say when the electrical activity is parallel, or perpendicular, sorry, it produces an isoelectric complex. So we know that it's not too uncommon in AVL to get a complex that looks like this. Equal parts up and equal parts down. And we're going to be able to use these relationships and this view, the different views of the heart, to start to put pieces together in various disease states. And so let's apply that to the leads. So we know that the electricity starts here in the right atria and ends in the left ventricle, so we get an electrical vector that looks like that. So what would we anticipate seeing in lead AVR? Well, since the P wave moves away from AVR, or the atrial activity moves away from AVR, we would expect a negative P wave. And since that ventricular activity is also moving away from AVR, we would expect a negative complex. And since most of the 12 lead is concordant, a negative complex equals a negative T wave. We would see AVL, a situation where the electrical vector kind of passes by. So it's not uncommon to have a biphasic complex. And we see that in lead 3 it's pretty similar. A little bit more of a dominant R wave, but a little S wave because as that electrical vector moves past that lead towards the left ventricle, it gives you that isoelectric component. we see in lead 1, the electrical vector is predominantly headed towards lead 1, so we get something that looks predominantly positive. Lead 2, similar story. That electrical vector is headed towards the view of lead 2, so again we get a predominantly positive complex. And again, AVF, similar to AV3, or similar to lead 3, but we see it's shifted a little bit towards that average electrical vector. So if we were to redraw it down here, we see the electrical vector moves similar to that. So we would expect a slightly more positive than negative in AVF. And so we can see when we talked in our last video that if we, for instance, see a situation where AVR looks like this, well, that's a little bit of a cause for concern, because that almost implies that the electrical activity of the heart has completely reversed. It's going from bottom left to upper right. Or for instance, if we start seeing lead 3 looking a little bit like mostly dominant, well, then that would suggest that the electrical activity of the heart is moving in a manner that is predominantly towards lead 3. And so we can use these views in our understanding of the average flow of the heart and how each view of the heart should perceive this movement. And we can start characterizing the flow of electricity through the heart, and subsequently which side of the heart is working more or which side of the heart is working less. And so now, since we have the limb leads down, let's take a quick look at those precordial leads. Well, if we look at the transverse plane of the chest, so we cut the heart right here, we get something that looks like this. And if we draw straight lines to the heart, I'm going to make it a little thicker. We see that each precordial lead looks at a different portion of the heart. And we already know this instinctively because we call that V6 and V5 the lateral view, because it looks right here. We say V3, V4 is that anterior view, it looks right here. And we say that V1 and V2 is that right ventricle septal view, because it looks right there. And then if we add another piece of the puzzle, and that's the average movement of the average electrical movement, we know it's from right to left towards the part of the heart that has the most amount of muscle. And so we see that the trend continues, that where the electrical activity is towards the leads, we get positive complexes, or predominantly positive complexes. And we know that predominantly positive complexes means we have a dominant R wave. And so we see that average electrical movement towards that V4, V5 range gives us those dominant R waves. And we see as we move away from those areas, our R wave decreases. Right? So let's look at V1. That electrical activity is kind of not opposite, but definitely the furthest away from V5, V6, so we get a dominant S wave. And that S wave, on average, decreases in magnitude until it disappears in that V5, V6 range. And the same is true for that R wave. Since V1 is the furthest away from the left ventricle you can get, it has a tiny R wave. And as you move closer to where the electrical vector is headed, our R wave starts to increase. And we see after V5, we move away from that dominant electrical vector. So V6 typically experiences a decrease in the R wave. So we know that that positive complex is a dominant R wave, and we know that those negative complexes equals a dominant S wave. So then the question becomes, well, what happens if, say, the electrical activity of the heart switches? What if, for some reason, we get a dominant rightward electrical vector? So say the right ventricle is working too hard, there's a pulmonary embolism, or we have right ventricular hypertrophy. How would that change the standard pattern that we see? Well, we can reason that since the electrical vector is now headed towards V1, V2, we might see an increase in their R wave in those leads. Or we might start to see a decrease in R wave in the lateral leads. And we might even see an increase in the S wave in those lateral leads as well. Let's have a look. So in this example, we have a dominant R wave in V1, and we know that that is uncharacteristic. And we see that V2 is very dominantly R waved, if that's a verb. And notice that V6 and V5 have dominant S waves. That's interesting because that's abnormal as well. Well, this dominant R wave in V1, V2 suggests that the electrical vector of the heart, instead of moving to the left, is shifted towards the right. And since V5 and V6 are the opposite view, their R wave is decreased and it's shifted over into the S wave. So that implies for some reason the electrical activity of the heart is shifted towards the right ventricle. And I've mentioned it a few times, but we should probably explicitly talk about it. There's this idea of this RS relationship in the heart. Or in the 12 lead, I should say. In opposite views, the R wave and the S wave are the same wave. Right? And what do I mean by that? So in this example that we saw, we know that typically V1 is little r and deep S, right? And we know, maybe I should draw it over here, right? We know typical V1 is little r and deep S, right? And we know that the typical V6 is little q, big R, no, forgive that QT prolongation, but we know that it typically has no S wave. Well, we see that when we shift that electrical vector away from V6 and towards V1, that pattern begins to go away. So we see that as we get a dominant R wave and a little S wave in V1, we now have a little R wave and a dominant S wave in V6. And that's because they're looking at the same activity but from opposite sides of the heart. And that's going to be a common theme we see, this theme of symmetry in the 12 lead, where if one view is giving you increased work in the right ventricle, which is causing the electrical activity, to flow towards the right ventricle. Well, then this means the electricity is flowing away from the left ventricle. And now that we now have a situation where electricity is flowing away from the left ventricle, and we said away equals negative, then we get increase in S wave in the away portion, and an increase in R wave in the towards. And so now we understand why when we see dominant R waves in V1, it's very characteristic to see dominant S waves in those lateral leads, because we've shifted that electricity away from those views. And it's going to be something that we look for when we start looking at disease states, is do we have that symmetry of pattern? Do those R and S waves match up in the different views of the heart? So, in summary, we know that the source is the SA node. And we know that the direction is towards the left ventricle. So we get that down and left movement. And we know that our RS relationship is really just seeing towards which electrodes and away from which electrodes is the electricity flowing. And from there, we can start asking ourselves, like for instance, if we see electricity flowing more towards that right ventricle, we can ask ourselves, well, why would the right ventricle be working harder? Or why is the left ventricle working less? Right? And so now we get to talk about some general trends. All right, well, let's have a look at some general trends that we can use to start to characterize some disease states. Like we said, a general trend that we have is that if you have increased work in one part of the heart, that's going to equal an increased amount of ions that are flowing, which is going to increase the amount of electrical activity. And that's going to equate to an increased wave presence on a 12 lead. And we can see that different parts of the heart have characteristically different parts of the EKG that show themselves when the electrical vector is shifted in that direction. So for instance, if we have an increase in amount of atrial activity, then we typically notice an increase in the amount of P wave presence. And that could either be P wave height, P wave width. Does the P wave start becoming biphasic or bimodal? And one of the trends we see in the right ventricle, when the right ventricle is working harder, or the electrical activity is affected at or near the right ventricles, we start to get those increase in R waves in V1 through V3. And we talked about that RS relationship. So if we get an increase in R wave in V1 through V3, we're going to get an increase in S wave in those leads that are opposite the right ventricle. And so that's V4 to V6 and lead 1. And the R wave is special in that, the right ventricle, in that those leads that look mostly at the right ventricle also peak a little bit at the septum. And one way this manifests itself is you're going to get an increase in Q wave in lead 3. Let's have a quick look back at, make sure we really are comfortable with these ideas. So if our electrical vector is shifted towards the right ventricle, we see that lead 1, the electricity is going to start moving away from lead 1. So we're going to get that away equals negative equals S. So we get an S wave in lead 1. If the electrical vector moves towards that right ventricle, then we notice that the right-facing precordial leads towards equals positive equals R waves. So we get an increase in R in those right-facing leads. And what's unique to lead 3 is that it has a pretty good view of the septum. So an increase in activity towards the right ventricle is going to towards lead 3, which tells us we have Q waves. Because the Q waves are representative of septal activity. Interesting. It shouldn't come too much of a surprise that if we have increase in activity in the left ventricle, well, we're going to see the opposite. So we're going to see a decrease in R wave in V1 through V3, an increase in S wave in V1 through V3, and an increase in R wave in V4 through V6. So let's look at an example. Here we see in V1 we have those dominant R waves, uncharacteristic of normal pathology. And we see we have those increasing S waves in the lateral leads, which typically that V5, V6, they don't have S waves. So this implies that the electricity is shifted towards these leads and away from these leads. And so something is happening inside of the right ventricle. And then if we look at these precordial leads, we notice something interesting. We see that the AVR that looks at the right has a dominant R wave. AVL that looks at the left has a dominant S wave. So again, that implies that electricity has been shifted towards the right. So all of this suggests to us that we have an increase in the right ventricular activity. Because we remember, increase in electrical activity of the 12 lead equals increase in muscle work. And so from just these few observations, we can ask ourselves, well, why would the right ventricle increase its work? And that'll be a topic of discussion for the next video, but we can see how easily we can ask ourselves the right questions by looking at the right things on the 12 lead. And one of the trends we want to be able to keep in mind is that repolarization of the QRS complexes, redistribution of the QRS complexes, well, they represent depolarization changes. And that depolarization is the same as the squeeze of the heart. And those depolarization changes, or those changes associated with the squeeze of the heart, well, they cause changes in the repolarization, or that relaxation of the heart. Now the difference is those repolarization changes, they don't really manifest as QRS complexes as they do manifest as those ST and T wave changes. So for example, if we have an area of the heart, say the right ventricle, that's being affected by an MI, well, the electrical flow of the heart is the same. It's still this way. But when the heart goes to relax, there's going to be a black hole of depolarization where the infarct is. So we're going to notice ST changes both in that area and those leads facing that right ventricle. So maybe V1, V2. And we're going to notice ST and T wave changes on the side opposite the heart. So maybe 1 in AVL. So in order for a disease to appear on the 12 lead, it has to alter the electrical movement of the heart. And since 12 leads read the electrical movement of the heart, all reading a 12 lead is figuring out, one, the source and destination of the electricity. How is it flowing? And what pattern, when we look at the flow of electricity, which pattern is that most characteristic of? Which pattern does that represent in terms of the disease? And that's going to be the topic of our next video. And if you guys would like, you can head over to the video 3 examples video. There we're going to be going over a few 12 leads to start to gain familiarity with some of these concepts. And as always, I look forward to seeing you guys at our next video, video 4, where we're going to start looking at patterns of diseases. And I hope to see you guys there. And good luck with your studies. Let's go ahead and have a look at some examples.